Okay, now for this transformation from R2 to R2, which is illustrated here, several characteristics of the transformation are illustrated by this example. Here's our transformation. And as we can easily see, if we apply this transformation to a vector x1, y1, and then to a vector x2, y2, what we get is the transformation applied to this vector plus this vector. Okay? In other words, if we add these two vectors and transform it, add the vector that we get, the sum of these two vectors, transform the sum of these two vectors. It's the same thing we would get if we transform this vector, and then add them. Okay. That's the property of linearity in essence. There's another condition for linearity, the transformation of any multiple of x1, x2, or x1, y1 will be that multiple of the transformed vector. But just taking this one property, the other property is easy to see and easy to prove. We illustrate that using just the vectors 1, 0, and 0, 1, which form a basis for R2. And we get this, okay? T of 1, 0 plus T of 0, 1 is T of 1, 1. And T of 1, 1, if we just plug 1 and 1 in for x and y in the definition, gives us 4, negative 1.2. T of 1, 0 plus T of 0, 1 is what? Well, 1, 0 maps to 0.7, negative 2.1, easily calculated. T of 0, 1 maps to negative 0.3, 0.9, again, easily calculated. And when you add these two, you get the same thing you did up here. So, applying the transformation to the sum of these two vectors, 1, 0, and 0, 1, gives you this. Transforming this vector, and then adding up the result gives you the same thing. And it's easily proven that this works in general. If you just take the symbols here and apply the given transformation, and you could apply any linear transformation, you're going to get the same result. Okay, so you got vectors over here. You got two vectors over here. It doesn't have to be 1, 0, and 0, 1. Got two vectors over here. You add them. Then you transform the added vector, and you get some vector over here. Now, if you transform this vector, you get a vector over here. If you transform this vector, you get a vector over there. And if you add those two vectors, you get the same thing you got when you transform the sum in the first place. You got to work through a few of these before you really completely grasp that, but there it is. Now, as we understand, the transformation that we're given can be represented by a matrix. So that the transformation of 1, 0 is this matrix product of the matrix with 1, 0, and transformation of 0, 1 is again the matrix multiplied by the 0, 1 vector. And that has to equal, because of the properties of matrix multiplication that we're very familiar with, that has to equal what we get if we multiply this matrix by the sum of these two vectors. This is guaranteed. We don't have to do the calculation to prove it. And it's guaranteed no matter what these two vectors are. Okay, whatever these two vectors are, you transform the first vector, you transform the second vector, and you add them. You get the same thing as if you add the two vectors and then transform them. And that's the simple property of matrix multiplication that says if you transform V1 and transform V2, same thing as if you add V1 and V2 and then transform it. Or if you multiply V1 by a matrix and V2 by a matrix, same thing if you add V1 and V2 multiplied by the matrix. Okay, so this is a property of linearity. So this is one property of the linearity of A, which is equivalent to the linearity of the transformation T. So this represents say if A represents the transformation T, then T is linear, pretty much. There are other properties of linearity. A applied to CV equals C times A applied to V. So I'll just say here provided A satisfies the other. Properties of linearity. Okay, so what we're establishing here is, and not just for the specific example, this is a theorem. Not going to go through the proof of the theorem. If you understand everything we did here, it's pretty easy to write out the proof of the theorem. If you can represent a transformation T by a matrix in this sense, the transformation has to be linear. And of course, if the transformation is linear, it can always be represented by a matrix. So everything that we know about matrix multiplication can be applied to the transformation.